Determining age of rocks. If you were to find a fossil, two questions might come to mind. What is this fossil of, and how old is it? In the previous section, we've already talked about comparing fossils found in different ages of rocks. This is called relative age, and it gives scientists a good idea of which fossils are older than others, but it does not give the exact age of the fossil. Absolute age of a rock is the number of years since the rock formed. While getting an exact number correct is probably impossible, geologists can narrow it down within a certain number of years. Now picture walking through the Grand Canyon, or just imagine it. You can even pull it up on the internet if you want to look at it, and you're going to see different layers of rocks determined by different colors, showing the different forms of sedimentary rocks that have been deposited over millions of years. Now, when we talked about the layer at the top being the youngest and the layer at the bottom being the oldest, this was discovered through the law of superposition. According to the law of superposition, in horizontal sedimentary rock layers, the oldest layer is at the bottom, and each layer is younger than the layers below it. But there are other clues beside the position of rock layers to help determine the relative age of rocks. These include extrusions and intrusions, faults, and gaps in the geological record. Recall that igneous rock forms when magma hardens. Lava that hardens on the surface is called an extrusion and is always younger than the rocks below it. If magma cools below the surface and pushes into an area, this is called an intrusion. And an intrusion is always younger than the rock layers around it and beneath it. Both extrusions and intrusions help geologists understand the relative ages of different types of rock. Geologists also study faults or breaks in the earth crust. A fault is always younger than the rock it cuts through. In order to determine the relative age of a fault, geologists find the youngest layer cut by that fault. However, sometimes this is hard for geologists because, as you know, faults move. Therefore, rock layers may no longer line up. There are also gaps of information in rocks, and this is because even though some rocks are deposited and build upon one another, we also know at the same time erosion is occurring, and so younger layers might erode away, exposing older rock surfaces. And if these younger layers are eroded away and new deposition begins building again on those old rock layers, now we have a surface where new rock layers meets much older rock surface beneath it. And this is called unconformity, which means it's showing a gap or a loss of rock layer information due to erosion in the geological record. When geologists give a relative age to the layer of rock at one location, they have to find matching layers of rock at another location so they can start dating rock layers. To help match rock layers, certain fossils called index fossils help them. An index fossil is a fossil that has to be widely distributed and represents a type of organism that exists only a brief time in the geological timescale. If you look at this image, can you find an index fossil? What you want to look for is a fossil that is widely distributed, meaning it occurs in a wide array of locations and it only occurs briefly. Well, first we can rule out trilobite because even though it lasted briefly, it did not occur in a wide distribution of locations. We can also rule out gastropod as being an index fossil because even though it was widely distributed, it has lasted through all the rock layers. But what about the ammonite? Yes, the ammonite is a perfect index fossil because 1, they are widely distributed among the locations, and 2, they only occur for a brief period of time. So geologists would now be able to identify the ammonite in each location and would be able to date that rock layer at each location and give this rock layer a relative age. When scientists want to determine the absolute age of rocks, they use what is called radioactive dating. Remember that the absolute age of a rock is the number of years since the rock formed. In radioactive dating, scientists have to first determine the amount of radioactive element in a rock. Now, before we go further, let's do a quick chemistry review. All matter, including rocks, are made of tiny particles called atoms, and when all the atoms are the same, the matter is an element. Elements include carbon, oxygen, hydrogen, and iron. And most elements are stable, but some elements are unstable, which means that over time these elements break down or decay by releasing particles and energy in a process called radioactive decay. The unstable elements are therefore called radioactive. Now, radioactive elements occur naturally in igneous rocks, and scientists can study the rate at which elements decay to calculate a rock's age. A radioactive element has a constant rate of decay. Therefore, when a radioactive element is halfway decayed, that time it takes, or the rate of decay, is called the element's half-life. So, an example of a scientist dating a woolly mammoth they found, it is known that all plants and animals contain carbon, including a radioactive form of carbon called carbon-14. Now, when a scientist measures the amount of carbon-14 left in a woolly mammoth, then they can determine its absolute age. But carbon-14's half-life is only 5,730 years. So for this reason, it is not a very good indicator to date very ancient fossils or rocks. Therefore, scientists often date rocks using what is called potassium-40. Potassium-40 decays to its half-life at 1.3 billion years, and they have used this to date rocks and know that the Earth has been around for billions of years. Okay, let's take a break. It's time to show what you know.